At this point, we know that charges produce electric fields. So I want to investigate a few different types of charge distributions, geometries, and see the kind of E fields they produce. And we'll start with the simplest one, or the one that we're most familiar with, which is point charges, which follow an inverse square law. And so consider in your mind's imagination an electric field gun that I have pictured here that, well, it's not really shooting charges out, but it's shooting out electric fields from a point charge. And that's real helpful, right? Yeah. All right, so as this thing diverges out, we have a E0, an E0 here. Now, at radius r, distance r away from that charge, we'll call the electric field this. And when we go double the distance, when we double that distance, the same amount of total quantity of field intensity over area, actually flux, it's a new term. Basically, it spreads out over more area. If you double the distance, it spreads out length, across and up and down. Double, so it's 4 times the area, so each patch has a quarter E0. Hopefully that makes sense. If we move it out not 3 times as far, then it would be 9 or 1/9 the intensity spread out over 9 squares. So the formula is that E is proportional to Q over R squared. Proportional to the amount of charge, inverse square to the distance from a point. So to make that inequality, to make the proportionality an equality, you just multiply it by the K. This is the same K we had in Coulomb's law. And it's only the source charge we're interested in to determine what the electric field is someplace else. If there happens to be another charge there, that's fine. But its E field is not under consideration, so we'll consider it irrelevant, even though in some circumstances that may only be an approximation. In a similar way that the gravitational field of Earth out at the moon has nothing to do with the mass of the moon. We're not talking about the moon's G field. However, it turns out that mass of the moon does distort the mass of Earth, produces tidal bulges, and that changes the gravitational field in detail, small detail, produced by Earth. And charges do a similar thing, but we'll consider that we're talking about a point charge that's unalterable, okay, in and of itself. Now, what about a long line of charge? A long line or an infinite line of charge. So we consider a point in space. What's the electric field there? And we start with a patch Q1. It's a really small patch of charge. The charge is uniformly distributed along this line, and this patch is like a differential patch, to speak a little bit of calculus terminology. But in any case, just consider it a very small patch, small enough to be considered a point, in which case we have E1 from Q1. And from this long line, we can find a symmetrical point over here of charge, symmetrical about, an axis perpendicular to the line to that point. So here it is, and it produces E2, which looks the same but in a different direction. Now if we add those two vectors, simple vector addition, 1, tail to tip with the other, gives us, there it is, a vector that's straight up, actually perpendicular to the line. Now we could choose any amount of additional patches. Let's say Q3 over here. Q3 produces an electric field that's away from the point, and maybe it's smaller. But in any case, whatever size it is, partly based on the size of the patch used and the distance, we have a symmetrical situation over here. We'll call it Q4. Q4 makes an electric field symmetrical to E3, and in any case, all these additional patches will add up to give you a vertical line, a line pointing away from the line of charge. So each patch has a corresponding anti-patch which cancels one of the components. Notice that the x components, the horizontal components, are all canceled. And therefore, we can conclude that the E field, in terms of the geometry, is perpendicular to the line. And now we should consider what the strength of the E field is as well. So then let's consider the size of the E field produced by this infinite line of charge. And we're going to model it with a little patch like we had, but this time I'm considering this having some finite extent. It's not really a differential necessarily. It's small enough to be a point charge from the point of view of this location here, radius r away. So it's got q, but this q is like completely differentiable as well. In other words, we could chop it up into multiple pieces. In any case, we know that E0 is kq over r squared, because q is small enough to be considered a point charge. Small enough in geographic extent. Now we're going to double the dimensions. Double the dimensions. This time we have 2r, and we have two small patches, q and another q, producing, you got it, 2q. So we have 2q away from our point, which is twice as far away. Now, twice as far away, twice the charge. How does that going to relate in terms of the E field produced there? The answer to that question will allow us to conclude the nature of the E field produced by a line of charge. So here we go. The E field is, since they still can be considered points, kq, but the q is 2q over the distance, 2r quantity squared, which is 2kq over 4r squared, which is 1/2 of kq over r squared. Of course, kq over r squared is E0, and therefore it's 1/2 E0. We double the distance, the E field cut in half, enabling us to reach the amazing conclusion that the electric field produced by a long line of charge is proportional to 1 over r, inversely proportional to the radius. And now, let's consider an infinite plane of charge. So here's a plane. Don't fault me for the kind of poor perspective. In any case, this charge on the plane is continuous and uniform. This time we're going to have a little circular patch, and think of this as a cone region. All right, so we have a little teepee here, inverted cone, and so it has charge q, distance r away. And if we do the E field from every little infinitesimal point in here, it's going to be constrained. The little E field vectors are all constrained inside the cone here, which is the region of E field production from every little infinitesimal charge that Q consists of. All right, so hopefully I'm not being too confusing there. But if we take a little piece over here, producing this one, a little bit over here, producing this one, every other place there's always symmetry everywhere throughout that patch. So when we add all the E fields up, we get this, which is from this small enough to be considered a point charge region, kq over r squared. That's the size of it. Now, let's double our cone size. What I mean is, make it twice as wide, or twice as high. The angles are the same still. And r goes to 2r. What does this patch go to? And to answer that, before you just say 2q, remember this is area. The area hasn't just doubled. It's pi r squared. So the radius is doubled of the patch itself. And if you square that doubling, you get 4. So it's 4 times the amount of charge here, producing, just like before, this region where the E field infinitesimal vectors are all existing, producing an electric field that we can now quantify, because again, we're considering that this is small enough to be considered a point charge, so it obeys, well, it obeys the inverse square law for that little tiny region, which looks pretty big right here. Don't be fooled. So E is K 4Q over 2R quantity squared. And that gives us KQ over R squared, which is E0, which is a very kind of satisfying and perhaps not so expected, or maybe it was expected, discovery that the E field is not only perpendicular to the plane, just like the E field was perpendicular to the line of charge, although it was radially out everywhere. This was radially outward, you know, not just in one direction. But the magnitude of the electric field produced by the plane, as evidenced by these two different distances, r and 2r, perpendicular to the plane. You know, you're looking at a different distance away, and we discover that the E field is constant everywhere. So that summarizes point charges, line charges, and an infinite plane of charge. So that'll do it for this little segment of our electric field geometry. Until next time.